Anyway, welcome to the SETI Institute Noontime Seminar Series. And as many of you know, these seminars are recorded and can be viewed either on YouTube or at the SETI.org website. And with that fact in mind, we ask that you hold your questions, if you can, in reserve till the end of the seminar, so we don't, I guess, cause lots of dead space. Yes, you're welcome to my seat. Is the one behind you free? Anyway. Today we're honored to have as our guest speaker Kevin Zahnle from NASA Ames Research Center. Kevin is an authority on planetary impact processes and the evolution and accretion of planetary materials and planetary atmospheres. Kevin's been at NASA Ames for 20 plus years, and really over that period of time has contributed a vast body of literature to the planetary science and astrobiology community. Kevin got his PhD in the mid-'80s from the University of Michigan, working with a famous James Walker, and then came to Ames as I think an NRC fellow or postdoctoral fellow, worked at Stanford, and essentially been at Ames ever since then. In support of his work on planetary accretion and atmospheres and impacts, he does mostly modeling studies, and both ab initio and models using data. And in so doing, he's really an expert on understanding these processes in our solar system.
Percival Lowell, the founder of modern American planetary science, he had a planetology that he was a very popularizer. He was kind of, in some ways, he was the Carl Sagan of his day. But he was mad. That's the difference. In his planetology, worlds form hot and dry out as they age. And this is an example here of canaliform features. That's what Dr. Lowell called, Professor Lowell. He bought a chair at MIT. His brother was running Harvard, but wouldn't let him do that at Harvard. So he went across down the road a bit, and he bought himself a chair at MIT. He was Percival Lowell, after all, the Boston Lowells. And he called them canaliform features. That's actually a Schiaparelli map, but you can see the canaliform features. He saw them better than anyone ever saw them. And in his view, large worlds cooled slowly, and was still quite young in 1895 when he was writing. But in the moon, we gaze upon the last sad age of decrepitude, a world almost sans air, sans seas, sans life, sans everything, Bowdlerized Shakespeare. As the heat dissipates, the body begins to solidify, starting with the crust. For cosmic purposes, it undoubtedly remains... Stop laughing. It undoubtedly remains plastic, but cracks of relatively small size. Into these, the surface water seeps. It's Can you read that? Let's go back and do it again. Does anybody want to try reading this? Okay, we're going to try it again. I should turn off the microphone. I know, I made... Okay, we'll skip him for the present, and... When I come down, I'll try to get back to that. But you're not being very serious. This is, after all, for TV. We're doing this for TV. Okay, let's try it again. Into these, the surface water seeps. With continued refrigeration, the crust thickens, more cracks are opened, and more water given lodgment within to the impoverishment of the seas. He imagined that the oceans were subducted. He didn't use that word, he didn't know that word. But that's what he meant. And that is a very common picture of what people think Mars is even now. They want a lot of water on Mars. They cannot see it. Therefore, they bury it in cracks to the impoverishment of the seas. You've seen the pictures of blue Mars, you know. Now, Lowell, what's important for us is Lowell accepted Kelvin's chronology. The Earth cooled by thermal conduction. The thermal gradient at the surface, which is measured by going into mines with thermometers, and you work out the temperature gradient. You know the thermal conductivity of rocks, so you know what the heat flow of the Earth is. That's been measured. And then if the Earth cools by thermal conduction, you can work out that the age of the Earth is 25 million years. The Sun, shown by gravitational contraction. Energy conservation indicates an age of 25 million years for the Sun. This is because all the energy that the Sun radiates is gotten from the gravitational contraction of the Sun. It's called the Kelvin time, 25 million years. It's a contraction time scale with radiative cooling. Lowell accepted it because this coincidence is why Kelvin became so stubborn. He got the two numbers were the same. Therefore, he is right. And the geologists, with all this talk about ages and ages of rocks, they must be wrong, because physics showed that the age of the Sun and the age of the Earth were both 25 million years. Just a coincidence, I report, you decide. But if we go to the luminosity evolution of the young Sun, this will be one of the main things we have to worry about, is the brightness of the young Sun. The so-called faint young Sun paragraph. Whoa, I thought I had a pointer. On the lower axis, we have time in millions of years. On the left axis, we have solar luminosity, at both logarithmic scales. This is the first 3 billion years of solar history. You will note that when the Sun is very young, it is contracting and getting fainter. That's the Kelvin time. You're looking at the Kelvin evolution of the Sun over here. This, the Kelvin. There's a what? A stick? Oh, yeah, I sure there is. Oh, look at that. That's probably it. Let's try it. There it is. Because this is the Kelvin. That's the Kelvin contraction. When the Sun hits about 10 million years old, it's a small red star. And then it continues to contract internally. It clears up because all these metals and things keep sinking to all the opacity sources, all the density of matter keeps sinking to the middle. And it keeps shining. It's still shining throughout this period through gravitational energy. But as the stuff falls to the middle, it clears up. The air gets cleaner and the Sun gets bluer. So this is bluing. Until it hits about the current luminosity at age 30 million years, at this point, you start getting some nuclear fusion occurring. And as the nuclear engines take over, you actually cool down. Actually, you get smaller mostly. And you land at about 7/10 of the current solar luminosity at 50 million years, at which point you're now in balance between nuclear fusion and radiation to space. And then the Sun sits there at 70% of its current brightness. You can imagine how cold Earth would be. That's an important point for us. Early Earth is going to be dealing with a Sun which is only 70% as bright as now. So you would expect the Earth to be glaciated unless you do something different. So that's the expected state of the Hadean Earth, ice-covered. And then slowly, as the Sun fuses hydrogen into helium, its mean molecular weight increases, and that causes its luminosity to go up in a way that was shown well before the modern era by people like Eddington. And the luminosity of a star goes its mean molecular weight to the 3/2 power. I don't know why, but it does. Now, Earth's moon formed by the impact of a Mars-sized. Did I mention that? There was something here called the moon forms between 30 and 100 million years. That's the usual range. For a while, a few years ago, they were getting quite cocky in the geochemical world, and they were starting to think that they knew it's when this impact occurred, because they thought they were seeing hafnium tungsten differences that would allow you to work that out. But now they don't think that anymore. Now they don't know. They just know that it's probably closer to 100 million years. So you really should think of the collision that forms the Earth and Moon as the impact as a collision between two planets that have been around for a long time. So Earth's moon formed by the impact of a Mars-sized planet with the Earth. That's the current theory. The impact placed, I got to change that to 30 to 100. That was 4.5 billion years ago. The planet that hit the Earth seems to have resembled Mars in many ways, not just in size, including its internal volatiles. Is one of the things that it resembles Mars in more than it resembles Earth or Moon. And this is what happened to it from Robin Canup. There is it, the intruder. There is the thing that we will later call the Earth. So those are two planets hitting. The colors are the temperature, and that's a shock where they meet. This is a glancing blow. That seems to work best for this purpose. So what you see is it just it can sense what Pete Schultz would call decapitating. It rips a piece off the Earth. So we just walk it through. And I think the thought might be that this blob out here will become a moon. The recap of the arguments in favor of the moon-forming impact are the moon has a general composition of a planetary mantle. It looks like it's equilibrated with an iron core, but there is no iron core of the moon, or just a very tiny one. So the moon was made from the mantle of an evolved planet. Numerical simulations show that a giant impact will separate core from mantle. This can happen. Not all impact geometries will do it, but many will. And you need to do that, because you have to take the core out of the impactor and put it in Earth's core. The mechanics work out. The impact gives the right angular minimum energy of the system that you see now. That means that there's not another big impact afterward. This is the last one, because you can see it still. You can still reconstruct the geometry. If another big impact had occurred, you wouldn't be able to do that. All other theories are fatally flawed. This has been the most popular argument. I hate it. I dislike immensely arguments that assume that we know so much about the universe that we can rule every other possibility out. That is very arrogant. Our focus here will be on the Earth, not on the moon. This is the Earth 20 hours after the moon-forming impact. On the left, we have temperature. In colors, the red is the hottest color, and the yellow is pretty hot, and the blues are the coolest. And this is immigration. Again, it's all taken from Robin Canup's simulation. I actually just used grab and pulled them out of an Icarus PDF. And these are the immigrants. The red stuff came from the intruder, and the blue stuff came from the thing we call Earth. You will note that there is a very clear core mantle boundary here. The iron tends to go right on through and is hot. And the iron from the impactor pools on top of the core of the planet that it hit. The mantle gets quite warm. This part over here is still to get warm. You can see there's some more hot iron coming down here, and that will come in and heat up the rest of the mantle. And the mantle will get thoroughly melted in the course of this event. After the impact, you have a silicate vapor atmosphere. Not only is the mantle melted, the top of it is vaporized. It's 8,000 degrees, if you remember the colors. The interior is melted. Some atmosphere is lost, but the oceans are retained, at least according to most current theories. And the basic reason is that you didn't do anything to the other side of the Earth when the impact occurred. So half of the Earth is basically in shadow from the impact. And it never gets hot enough to lose the water. The day is about 5 hours long. The month is about 5 hours and a minute long. There is a moon. That's kind of the point. And Earth might have looked something like this. I've taken just an infrared picture of Jupiter, but it gets the concept across of fast rotating oblate with glow through silicate clouds. So that would be a visible image. That's what the Earth would look like to your eyes, roughly. Much of our quantitative discussion from now on will be based on 3 physical constraints. We're going to conserve energy, we're going to have a faint young sun, I've told you about that, and we're going to have a runaway greenhouse effect. Conservation of energy is really helpful. It keeps you from getting very, very wrong when you're talking about things you don't really know much about. The faint young sun is well established. It is so well established that the astrophysicists were right. They beat the physicists at their own game. They told the physicists that there was a mass of the neutrino, and the astrophysicists were right. Their model was more robust than standard model of physics. You've got to give the astrophysicists some points here. And we should take on, at this point, I take on faith they're right about the faint young sun. The runaway greenhouse effect is less well known than these two, but we'll talk about that. It's usually told as a cautionary tale to young planets. If you go too close to the sun, you're going to end up like Venus. This is the greenhouse. Now, I start with these cartoons. You go to the web for this kind of stuff, right? Tried and true explanations of how things work. That's where the web is good for, right? The facts. So here's a graph of the greenhouse effect, a picture of the greenhouse effect that I stole from somebody, I don't know who. The concept is you got the sun, light comes in, some of the energy passes through the atmosphere, and some gets reflected off clouds or scattered out of the atmosphere. Some is actually absorbed in the atmosphere too, let's not worry about that. Then what gets absorbed gets re-rated as heat. So Earth's surface is heated by the sun, radiates heat back out towards space. The greenhouse gases will intercept some of that heat and sends it back. And so you're warmer. Now, in the runaway greenhouse effect, you got a problem. You got too much solar energy coming through the atmosphere. Not enough of it's getting reflected. The amount that you can get out is fixed by the physics of water. And the explanation is fairly simple, but I don't necessarily think it'll be that easy to grab. But what it is that when you have liquid water around, you have a constraint, the saturation vapor pressure on water that relates temperature to the amount of water, to the column of water, because pressure is the column of water. Well, the column of water is also the optical depth. So you have a unique relationship between optical depth and temperature. That gives you a unique radiation to space. There is a number. It's about 310 watts per meter squared. It is a number. And the planet cannot radiate faster than that and still have liquid water and be in steady state. And that's the runaway greenhouse effect. So if you got too much sun coming in, the oceans evaporate and the surface heats up. And then, this is my computer model here, until it use a nice big red circle, and it begins to melt. And once it begins to melt, water will then dissolve in the melt, and you have a negative feedback that stabilizes your climate with a silicate melt surface. This is all sciencey now, a science graph. On the left axis, it's the same thing I just said with those, web-based graphics, but now we're just going to use one of these science type things with like axes and numbers and all that kind of thing. On this axis, we got the surface temperature. You notice I have a weakness for logarithmic axes. On this axis, I have another logarithmic axis, and this is awkwardly written as net insulation plus heat flow. And what you should think of it is, if you think of the Earth as a little star, and you think of thermal radiation from the Earth as its radiation, that's what that is. That's what that refers to. It's the total amount of heat radiation leaving the Earth. It's like its luminosity is the way to look at that number. The runaway limit occurs at 310 watts per meter squared. To the right of the runaway limit, you have a steam atmosphere with no liquid water anywhere. And I have the three steam atmospheres labeled by how much steam in bars. 500 bars of steam is like an Earth-like number. That's takes the ocean plus an ocean that you have hidden in the mantle, puts them both in the atmosphere. You get about 500 bars of steam. And that would be the temperature profile of an Earth. It would be like 2000 K during this phase. If you only have like half a bar of water, which might be a current Venus type number, you would be on this curve here. Now, Earth today is receiving this much sunlight after you've taken into account clouds. And it's pretty clear, pretty near the limit, but it's over on the left-hand side where you can have where CO2 matters and affects your surface temperature. I want you to focus also on 100 bars of CO2, 500 degree surface. There is 100 bars of CO2 readily available to the atmosphere. It's in carbonate rocks, it's in the mantle, but it's there and would have been in the atmosphere, I will propose, at that time. This is what a naked planet would do, by the way. That's just a ball, sigma t to the fourth. So to give you comparison, of what the thermal blanketing effect of an atmosphere is doing, which are these curves here. It's much warmer because of the thermal blanketing effect of the atmosphere. Now, after the moon-forming impact, the runaway greenhouse effect is going to run backwards. Earth's going to be hot, and it's going to cool down and run from right to left, with the trajectory something like this green line. So you're starting off with a small amount of water in the atmosphere, and most of it in the magma seas. And as the planet cools, it exalts the water, outgassing all along until you hit the runaway limit. When you hit the runaway limit, when it's cooled that much, you condense the steam, and you get an ocean. And the ocean will land at about 500 or 600 K, because you also exhaust 100 bars of CO2, because Earth's got 100 bars of CO2. And then eventually, the CO2 is put away again, put back in the mantle, put under the rug, put into the carbonates in the marbles that you may use in your bathrooms. Oh, I don't know. Got marble bathrooms? I don't. Home Expo Design Center went out of business because they couldn't sell enough marble bathrooms, I think. Until you get down to here. So Earth's first million years, I just described. I'll describe them again with a different graph. This time with time as my axis. And again, temperature, the same logarithmic axis that I'm fond of. On the right-hand side, I have reservoir sizes in bars. Bars is a number I like. 100 bars is the total amount of CO2 you've got. 300 bars is the total amount of water in the ocean. 500 bars is the total amount you've got on Earth. So numbers I'm comfortable with thinking about. The surface temperature goes to the left, and you've gone through a rock vapor phase that lasts about 1,000 years. And that's a conservation of energy type argument. And then you can start condensing. Your rock vapor all leaves the atmosphere. It rains out, basically. And you have these magma seas. And I think of them as, this is not the conventional magma ocean that you read about for the early moon or something. This is actually liquid, with waves. And you could make a boat out of pumice and sail around in your asbestos suit. The steam is exhaled through this period, and it's partly responding in a negative feedback fashion to the cooling of the system. And it maintains the surface temperature by exhaling the steam. You thicken your greenhouse effect, as it were. And so you hit the runaway greenhouse effect somewhere around 10,000 to 100,000 years and then chug along until about 2 million years, and then you're out of energy. An important point is that tidal heating throughout this is significant, because remember we made the moon, and it's only 3 Earth radii away when you make it, and then it gets tidally evolved outward. Now, the energy comes from taking the spin of the Earth, which is 5 hours a day, and raising that to 12 hours a day. Get that energy back through tidal dissipation, and that energy is all going to be deposited inside the Earth. And it's a significant term. It's like 1/10 of the energy of the impact, something like that. Now, when this hot phase ends and a more modern phase begins, depends on when CO2 gets subducted. And I don't know when. That's a topic that I have no real information on. But at some point it happens, because CO2 eventually becomes a minor gas. And now let's talk about what's inside the Earth. And I always, at NASA, at least during the previous administration, we taught the controversy. There are 2 theories of the internal structure of the Earth that are in play. On the left, we have the complete hollow shell model, complete shell hollow Earth model, in which there is a little internal sun, and there's the continents on the inside as well. You've read about this one, I'm sure. I have called it moronic design because there's nothing that would keep that star in the middle. Gauss's theorem will tell you can go anywhere in there. And so it would be like you'd have hot days when the sun got close. Conventional dogma is, you've all heard of that. It's like a core. There's an inner core. There's a mantle. They put a D double prime layer in there. I love that. We'll talk about that maybe. You got a crust. So continuing into the moronic design model, it's actually been mapped. Swang, I believe, is a place. I've never quite figured Akvatabar. You kind of wonder where Lucas got his names from. Plutosia, what does that say? Bill, that's a tough one. Then you got stuff out here you've heard of on the outside. You notice the holes are always at the poles, because they're hard to get to. So that's where the holes are going to be if you want to go in and out. Of course, another view of moronic design is that we, in fact, are on the inside, and that's what this is. See, the heavens are on the inside, you see, and we're all living on the inside of the shell. It's just that we've all gotten it wrong, you know. It's just we think we're looking out, but we're looking down. But now, get back to convention. Initial conditions, you've seen this before. A lot of hot iron on top of the core, a lot of hot mantle on top of the mantle. Hot, high, bright colors. Immigrants, red. So you end up with an interior structure that looks like this. And I admit that this is only a computer model in the limited sense that I generated the picture with the computer. The radius is on this axis, temperature on this axis. And we're not getting too specific anymore. These are the melting curves for the mantle and the core. You will note that the mantle has a higher melting point at the core mantle boundary than the core. That seems to still be thought to be the case, although this has always been controversial. It's known to be true at some level because the core is melted and the mantle's not. So it's a fact, but they always fight over the difference between this, the discontinuity and so forth and so on. The hot iron is pooled on top of the core, and so I have a hot temperature up here. A hot mantle is pooled on top of the mantle, and I'm presuming this is getting cooked down at the bottom. And then over time, the thing cools down along an adiabat in the mantle. It's convecting, while in the core, it's conductively heating to the interior of the core, because the interior of the core never really got hot in the impact, because the shock wave didn't actually reach that level. Eventually, we get into tidal heating. And I named this after our softball team. You have the mantle develops a dregs layer at the bottom and a dregs layer, a scum layer on top, basically. Stuff that doesn't fit into the crystal structure of the mantle, and this stuff is pushed out. And stuff that doesn't fit in the core will end up in this dregs layer as well. So you end up with this thing which will become the D double prime layer, and everybody talks about. The first place on the Earth that gets solid is at the bottom of the mantle, which is here, and that's where the tidal heating will first start taking place. Tidal heating is sort of, you think of the paperclip. That's the analogy you always want to think about when you think about tidal heating. If I were to take a cup of coffee, or this cup of water, and I take a little stick and stir it around really fast, it's not going to get hot. So tidal heating doesn't work in a fluid. If I have a really strong thing, I can't even bend it. There's not going to be any tidal heating. If I got a paperclip, I could bend it back and forth till it gets really hot. And that's where tidal heating takes place then, is in kind of weak solid. The first solid in the planet is here, so that's where the tidal heating takes place. And so you end up dumping a huge amount of the energy of the impact into the bottom of the mantle, which keeps the mantle stirred, which is an interesting thing. Tidal heating eventually climbs up through the mantle as the moon evolves further and further away and the Earth cools down. You degas CO2 and water. You get an ocean. You have a crust. This is after the magma the magma seas have frozen. The dregs layer remains full of all sorts of weird things. There is a negative feedback between mantle heating and tidal heating. Atmospheric thermal blanketing will control the rate the Earth cools. That was the runaway greenhouse effect. And therefore, the atmosphere is actually laying out the, belaying is the word, I think? What do you do when you take a rope and let it out? Anyway, it's belaying, is it? Yeah. That's what I meant to say. Okay. Anyway, the atmosphere is doing that to the moon. The moon's on a rope, and it's being let out, slowly but surely. Pictures of what it's now. Let's not talk about that. This gets into what the properties would be of a magnet sea at its surface. And we won't talk about that too much other than the heat flow through the early Hadean is Io-like, as opposed to, I was going to get into technical stuff, but what time is it? Yeah, maybe I could talk a little bit about this. Anybody interested in this stuff? Okay. Plate tectonics doesn't seem to work for heat flows bigger than about a tenth or 2/10 of a watt per meter squared, which is Earth-like. Higher heat flows seem to require a different geometry of tectonics. If you want a high heat flow, the best thing to do is to have volcanoes and just erupt lava on the surface and let it cool to a low temperature. That's very efficient. So that's the most efficient way to cool a planet. That's what Io has chosen to do. And so as an example of an Io-like object, I'll show you Io, which is an example of heat flow at 2 watts per meter squared. But it's not really right for Earth. The problem with Io is that it's too small to be a good analogy to Earth. Io actually, at its core mantle boundary, you're just getting pressures high enough to begin to cause basalt to undergo what is called the eclogite transition. What happens is basalt is what we have on the seafloor, right? And that's what subducts. And it's not that dense. But if you get it to a certain depth, in Earth that's about 150 kilometers, it squishes into a different structure that's dense, and then it will sink. Io doesn't have that. And so it's kind of hard. It's not actually possible. Apparently, Io can't actually differentiate its mantle very well. And it seems to be pretty well mixed. So it's probably not what Earth will do. Norm Sleep thinks this is what Earth will do. And he devised something he called a mush ocean. So now the Earth is encased in basalt that's 100 kilometers, 150 kilometers deep. But it's warm. And it is so warm that it circulates quickly and easily, so that it's basically permeable to heat flow, so that the mantle will be controlling the heat flow. And this mush ocean, which will look like rock to you, will still be very pliable and easily lets the heat through by its convecting within it. The only thing that it doesn't change anything from our perspective on the surface. It's actually a very good way to process basalts and make protocontinental crusts and so forth. Well, I just bring that up to suggest that at least Norm has been thinking about how you get around the limitations of plate tectonics. Now, there's a little bit of evidence for the Hadean. The main little bit of evidence for the Hadean are zircons. The oldest surviving bits of Earth are zircons found in some 3.2 billion-year-old rocks. I think there's now some seen in Greenland as well. These rocks are from Western Australia. Some of the zircons had been bouncing around Earth's crust for 1 billion years before they got caught in these rocks, which are 3.2 billion years old. So the zircons are these tough little crystals of zirconium silicate. That's its structure. And they're tough. They really are tough. And they have the huge advantage that they incorporate uranium and thorium quite readily. But they do not incorporate lead readily. So you can then use your uranium lead or thorium lead dating to get an age of the zircon. So zircons are wonderful. They last forever. And they have clocks in them. One thing that always confuses me, these are millions of years, these clocks. And those numbers, I believe, are the error. So you have 4.26 billion year zone, a spot here. You have another spot here, this is 4.03 billion years. You have another spot here, which is 3.676 billion years old. And the guys who study these things believe all these numbers. They think they all refer to different episodes in which the zircon got a little bit subducted, got kind of dunked in the mantle and got quite hot, but then came up again. And as part of its bopping around in the Earth's crust. It's not just going from beach to beach. It's actually going down into the crust and then coming back up again, but not getting destroyed. That's the idea. The core of this one, I love these things. This is the typical zircon. Actually, of course, it's not the typical zircon. It's their oldest one, their single coolest one. It's the one they show is their typical one. And I don't blame them, right? This is the cool one. 4.32 billion years old. That's pretty old. And the zircons are kind of granite-like. They kind of belong to the crust. They're made of, because zirconium is very incompatible. It's +4. Things that are +4 don't fit in well to the mantle, except silicon, of course. Oxygen isotopes tell us that the zircons were forged from rocky debris that had been altered by liquid water. This is something you'll read in a lot of papers. People have been studying this for quite a while. The key point is that a zircon that comes from the mantle will have an O18 excess of 5.5 per mil. A zircon, which they call supercrustal, and I'm afraid that word supercrustal is not something I understand. I can't translate it. It's geology speak. But it's got something to do with continents or something. And they have higher O18 that requires that they interacted with water. Water has a very high O18, and it weathers these things and impregnates the rocks with the isotopic signature. So this is inferential evidence that you had crustal silicate crusts, granitic-like crusts. That's what they always want to use. They always want to say granitic-like crust. Although I don't know if any of these are really granite-like. That's an all-out granite right there. So why did I put that up? Oh yes, cold. Cold. I wanted to get back to cold. 7/10 current brightness. It's going to be cold outside. But before it gets cold, it's hot because we've cooled down along this curve. Here's our trajectory again. 100 bars in the atmosphere. Again, temperature. I've dropped the logarithmic axes here just for clarity's sake. And here we have that weird unit that I should have called Earth's luminosity here. I got it labeled with planets, familiar planets. Earth 4.4 billion years ago with different albedos, or these dotted curves here. Earth now. Venus 4.4 billion years ago with a lot of albedo would be here. Venus 4.4 billion years ago with a little less albedo would be here. You'll note that Venus is undecided where it initially landed with respect to the runaway greenhouse. So that's, for people interested in Venus, this is a very interesting thing to think about, is what was Venus like when it first formed? Was it Earth-like, or was it Venus-like? We don't know that. So on this graph, I've got Earth coming along with 100 bars of CO2 in the atmosphere, which is also a Venus-like total, trundling along until it hits 40% albedo. I've assumed that it's cloudier for some reason. I don't know why I picked it, just did. It's 500 degrees at the surface at that point, and you ask, what is the composition of the atmosphere? This is what Hashimoto et al. Say it is. I think that Schaefer et al. Say it's not this, it's something else. So the experts are fighting amongst each other, calling each other idiots, as they often do. But I'm just going to use this one because it's been published, and I could grab it out of the article. And this temperature here would be the temperature at the surface of the Earth after you've first rained out your steam in the Hadean. And according to this graph, there is a lot of methane in that atmosphere. It's 10% methane. That's quite interesting, isn't it? I think it's quite neat that it could be 10% methane. Anyway, it's way out of equilibrium of what you would have at a lower temperature. I just wanted to focus on the methane there. Potentially a lot of methane, although very sensitive to the temperature. I cannot reproduce their calculation. I don't really know if I believe it, but that's what they would have you think. Carbon monoxide is another interesting gas that's out of equilibrium. You could have quite a lot of that at 500 degrees. Could be 0.1%. tenth of a percent is getting quite poisonous, actually, for us. Cigarette smokers like it, though. That's what they get, right? They get 300 ppm in their cigarette. It contributes to their high. Earth's trajectory is to take the CO2 out of the atmosphere and put it in the mantle, or put it in continents, or put it somewhere. Don't know where it goes, or how quickly it goes. But that, I've just drawn a line to move it down to a point where you're down to a tenth of a bar of CO2 in the atmosphere and you've hit the freezing point. And then you get into this, the problem that Earth would face if it got rid of its CO2 is that it would be very, very cold and you would be ice covered. And then once you're ice covered, your albedo goes way up and you'll end up way down there at 230 to 250 Kelvin as your surface temperature. This is a model of what that planet might look like. That's just the first approximation. Years ago, I did a model, a photochemical model. I tried to figure out what the composition of that atmosphere would be, and it never converged. It just kept converting CO2 into CO. Kept making O2 and CO out of it, because it's very cold and very dried. That was a bad model, but that's my model, I can say that, bad model. But the basic idea that CO will build up in a cold, dry atmosphere is correct. I want to emphasize carbon monoxide again. It's a very interesting gas. Another thing that's happening when you're in this state, potentially all ice covered, is that things are hitting you. They're hitting the moon. There's an example of something hit the moon. I mean, you don't actually see the thing that hit the moon. You see what it did after it hit the moon. And things like that are hitting the Earth too, and they will make temperature very, very high. And so this is like an example of what one of those kinds of things would do on Earth. You got temperature here on this axis. You would quickly jump to, your atmosphere would get like to 2,500 and then cool off to maybe 1,500 over days. And then it's cool off from there over weeks. It's not a huge deal, but still the whole atmosphere would be 1,500 K for a short time. And what makes that interesting is that the atmospheric composition will come to reflect that, and then it will be quenched in at that high temperature. And at that high temperature, there's a whole lot of CO. A lot of your CO2, like half of it, has been converted to CO. There's also a lot of H2. And these things can be quenched into your atmosphere by these shocks. It's like lightning on a global scale. That's interesting because of the CO part. Back to CO. Life on CO. I like CO. CO's cool. There are carboxydotrophs. These are guys that eat carbon monoxide with water to make CO2. There's an example of one. Rhodospirillum rubrum. That must mean red. Rhodo seems kind of red too, doesn't it? Not really clear. Maybe it's like the red spiral bacterium that won a Rhodes Scholarship. Bill Clinton might, maybe. Methanogenesis is another thing you can do with CO, is you take CO and water and you make methane and carbon dioxide. You make a living off of that too. Methanobacterium thermoautotrophicum is one of them. And that's the bottom line, they eat water. So you got CO, you got water, you can eat that. CO is interesting. It's free lunch. Better than peanut butter, I think. A little more poisonous. I don't like, I'm kind of allergic to peanut butter. It's probably in the same league. What modern methanogens do, I've just grabbed this out of a paper by Ragsdale. They call it the Woods-Lundahl pathway, and it's supposed to be, it's like a different way of fixing carbon than the Calvin cycle or the other ones you've heard of. It's just this thing that methanogens do. Unfortunately, I never quite understood what the plug was about and the wire. But the key thing, from my perspective, is that you take the CO2 and you make it in the CO, and then they put it in a tube. They bounce it down this tube like a ball. They won't let it out. A lot of these guys can't live on carbon monoxide at all because carbon monoxide is so precious to them once they've made it. They've invested a lot of energy into taking a CO2 and making a CO out of it, that the CO is precious now. So they put it in this tube and they won't let it out. And it trundles down the tube until it hits another enzyme, and then it goes do stuff with the CO. So the CO is the thing they actually need, is the thing they work with. So the CO is precious. It's passed down the tube. Both of these enzymes, and don't ask me what they stand for anymore. I think I once was able to say those things. Now I can only look at the acronyms and repeat them. CODH, ACS. They use nickel iron sulfur cubes. They're little nickel iron sulfide cubes. It's like four irons, a nickel, and 4 sulfurs in these little cubes. And that's what they use as their catalytic converters to make the CO, to hold on to the CO. Because nickel and CO have a very strong affinity. And you can grab a nickel. It's more strong than iron. You know, iron has a strong affinity for CO because if you breathe CO, you die, you turn blue. Because the CO has replaced CO2 in the hemoglobin. It's grabbed onto the iron. Nickel has a stronger affinity for CO than that. Nickel has such a strong affinity that nickel tetracarbonyl, NiCO4, is a stable gas at room temperature. Very poisonous, as you might guess. But it's a gas stable at room temperature. So the other thing was carbonyl sulfide, the last of the gases I was interested in. This is something you get when you have extra sulfur around with CO around. You'll get carbonyl sulfide. And in 2004, Liman, Orgel, and Gadiri pointed out that you can use carbonyl sulfide to mediate prebiotic formation of peptides. It's a condensing agent. They point out that people hadn't been thinking about this, but it's worth thinking about as a prebiotic compound. I want to remind you again, this time carbonyl sulfide. It's another thing that you get from these shocks at pretty high amounts. We conclude. The moon-forming impact separated the volatiles from the mantle. You may have read this in another book, famous old book, about separating solids from liquids and volatiles and so forth. The magma seas lasted for 2 million years. The cooling rates determined by the steam atmosphere, the thermal blanketing effect thereof. The rate of lunar orbital evolution was determined by the steam atmosphere for the first couple million years. After that, they decouple. And the moon will be maybe 15 or 20 Earth radii away by then. Tidal heating was important for 100 million years or so. As important as radiogenic heating, or more important than radiogenic heating. In that sense, Earth is IO-like. After the steam condenses, you have about 100 bars of CO2 left in the atmosphere, I think. That's just 100 bars is what you see on Venus. 100 bars is what you see. You count up what you got in the carbonates and in the mantle, so why not 100? That seems like the right number. The surface would have been 500 K. Cooling then thereafter depends on when the CO2 enters the mantle. This could have been as less than 10 million years. Norm Sleep thinks it could be as short as a few million years. Or it could be more than 100 million years. We don't know. Hadean heat flow may have been handled by means other than plate tectonics. Whoa! The asymptotic Hadean climate ought to have been cold. I don't have a solution for that. You would need greenhouse gases to have a solution to that. Big impacts triggered brief impact summers. They didn't talk about that, but of course they did. You saw the high temperatures that you got after the Mare Orientale impact. So you would have impact summers even if you had an otherwise ice-bound Earth. Hadean chemistry can be prebiotically friendly. Carbon monoxide is easy to make in huge amounts in quantities that are far from equilibrium, and I think is likely to be important to prebiotic evolution. And finally, life puts Earth under new management. I didn't talk about that, but we're managing climate now, and we're doing a heck of a job. Epilogue. Whatever did happen to Venus? I'd like to end on this. I like Venus. One possibility is it had its giant impact, presumably it did, on a dry evolution. Or imagine it didn't have enough water, or the albedo was kind of high, or somehow or another it ended up on the wrong side of the runaway limit from the start. So it's cooling down, chug, 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 and it lands on the wrong side of the runaway limit. You never get a liquid ocean. You just slowly fritter away your water, one hydrogen at a time to space, and you end up where Venus is now. A lot of CO2 in the atmosphere, 750 degree surface, not much water. Solid crust. It's one possibility, pretty boring. Another possibility, much more interesting, is that it does reach the runaway limit and it does rain out the water that it would have had in its atmosphere. The water rains out and it starts doing what Earth did. It starts to chug along this 100-bar curve till it hits an equilibrium with insolation. It's closer to the sun, it's going to be warmer. And because it's over here, it just ends up doing this little loop over maybe 1 billion years. never really gets cool, but it could be a hot ocean, a 500-degree ocean, perfectly plausible. But it wouldn't be a 100-degree ocean or a 10-degree ocean or anything like that. Until as the sun brightens, it lands back on the runaway greenhouse. And now this time, it follows that trajectory. It ends up going through the frittering away the water again. I don't know whether you reach the melting point or not. I decided just by fiat, I'm in control, it's my computer. I didn't let it quite reach the melting point. And that's my other Venus story. Dry Venus, wet Venus. Quite different. And the water escapes into space. The maximum speed a molecule may attain, Clerk Maxwell deduced from the doctrine of chances to be 7-fold the average. What may happen to one must eventually happen to all. Thank you.
Thank you for your time.
You're welcome.
Questions?
Hi, Kevin. I was fascinated by your last two slides there. I wonder what technically feasible
You slept through the
means.
rest of it?
Well, in particular, you know, in terms of why do we study the planets, the story
Yeah.
of Venus and how it's related to climate change on our own Earth, are something that I find very easy to explain why we should have taxpayer science in this area. But what...
Tell it to Weiler.
yeah, good luck. But what technically feasible means could you establish to determine the difference between these two hypotheses with
Well,
the kind of technology that we have now?
This one is, I think, quite unlikely to lead you to proper continents and granites and so forth. I think you need liquid water for that, in my opinion. Apparently not everybody's opinion, but in my opinion. There are people who think that water vapor will react with rock and then subduct. I think that's ridiculous, but you know, I was only the referee on the paper. I only said 3 times I thought it was ridiculous. Nature will publish it. Anyway, without any support, just another unsubstantiated assertion in nature. Never happens. This one will produce a very Earth-like rock cycle. So you will get granites. You will get continental materials. And that's a straightforward observation. You just need to go there with a couple of landers. I think would be sufficient. They're trying to, I know Venus Express people have claimed that they have sort of got an argument for determining that they have granites that they see from space. I think that that's the kind of thing that is intriguing. But I don't think you can really answer that short of landing there with David Blake's instrument, an X-ray diffractometer. That's what you need. You go there, you look at the crystals and say, ah, granite. That's the way you got to do it. Other than that, you're just inferring. You're just guessing that Maxwell-Montes is granitic. Looks like it is. Could be. I think it's likely to be, actually. But you got to be able to prove that. Because it's kind of it's a big point. If you can have a planet that's totally... You can have a planet that's habitable. Oh, that was Weiler again. He doesn't like this science stuff. If you... Oh, I lost my train of thought.
You were saying it's a big point to know for sure.
Yeah, it is, because it would have been it would have been habitable as far as we understand habitability, or potentially habitable. It might have been too hot. It's hard to know. That's pretty hot, 500K. It may be it's physically impossible for life, carbon-based life at 500K. I don't know. And the highest temperature you see on Earth is 400K for life. There may be 390, something in there. So maybe you don't get quite cool enough. But you know, from the point of view of habitable planets, that's really pretty interesting. To imagine that Venus might have been once habitable. And if it's got rocks left over from then, which if you have granitic continents, you probably do have rocks left over from then, go take a look at them.
Kevin, it's probably worthwhile to point out that with the next generation of 30-meter telescopes with infrared coronagraphs, these steam post-impact worlds are pretty easily detectable
Oh,
there's
yeah.
enough young stars in the solar neighborhood that, given the
Yeah, these are
statistics, you might be able to see
that's a
them.
good point. These guys are detectable. Where's an example of one of these detectable guys? No, not that one. Go all the way back. Back. Oh boy, it's way back there, isn't it? These guys. This is potentially quite detectable, yeah. Because the light that comes out will come out through the holes in the water bands. It'll be the hottest, and it might be detectable. Be cool. A couple million years is a reasonably long time. You get a bunch of Earth-like planets. You start getting a statistically good chance of seeing one. Good point.
Hi, Kevin. So one of the older kind of ideas about Venus was that it hadn't had a giant impact, and that signs of that were that it still had its thick primordial atmosphere, and it had, you look at its rotation rate, and it had no moons. That those were all claimed to be signs that it hadn't had a big impact like the Earth had. Do you still agree with that?
I've never agreed with that.
Okay.
Yeah. I think it's just unlikely. It's just hard to see. How do you make such a big planet without having big things hitting it? It just seems very unlikely. Most of the geometries you take for a moon-forming impact will not give you a moon. They're either too fast or the angles are wrong. And so getting a moon is like a 10 or 20% chance. It's by no means a given that you'll get one.
What does Hadean mean?
Hadean is the geologic term for the time before the first rock. That's the original definition, but it moves around. Definitions, it was invented by Preston Cloud, there was originally something called, you know the geological time scale at all? There was something called the Archean. And he had another one, he had an Azoic before that. So the Archean was beginning at the first fossils and then going on. No, I got that wrong. Let me get this clear. There was something called the Proterozoic, which begins with the first fossils with life, any sign of life. And that dates to about 2.5 to 2.8 billion years ago originally. And before that, there was this concept of an Azoic, the lifeless Earth. And then eventually they started finding evidence for life during the Azoic. So Azoic would no longer cut it. So they broke that, Preston Cloud broke that into an Archean, which goes back to a biblical word having to do with beginnings. And before that, this time before any rocks, which he imagined would be hellish, so he called it the Hadean. And the name stuck. And the Hadean now is defined as either before 3.8 or before 4 or before the end of the late bombardment, depending on which authority talks about it. There is no official definition right now. But of course, there are committees of authorities debating these matters in Capri and places like that.
Next question. I have a question. So, well, two things actually. Could you describe briefly why the moon-forming model or moon impact model requires sort of a glancing impact as opposed to a higher angle? And let me just finish the other question.
If it's too glancing, it doesn't work, and I think you don't get a moon or something. I don't actually know why, if it's too glancing, it doesn't work, but you need a certain angle. I know. If it's too glancing, you end up with too much iron in the moon. You want to separate them. And if you come in straight on, you don't get a moon at all.
Oh, okay.
And so you need to do it at kind of the right angle. 35 to 45 degrees is what the more recent computations get. But these things change because they're undoubtedly highly dependent on the specific properties of the numerical code that are being used.
Right, and with that thought in mind in terms of dependence on model parameters, I wondered how does atmospheric stripping or things that might have occurred during this period of heavy bombardment, how would that affect?
The thing about the moon-forming impact that makes it bad for stripping an atmosphere is that it's a low velocity impact. It has to be a low velocity impact to get the moon.
But how about later on, once you
And
have
if they're
fluid-
high
fluid
velocity
separation?
impacts, you will get a hotter initial condition. You may be able to lose more atmosphere that way. I don't know. But for the moon forming impact, you don't even, the impact is not high enough velocity to get the atmosphere hot enough to just evaporate. So the only thing you're going to get, only stuff you're going to get rid of is the stuff that you actually just hit and push out.
Okay, and how about for post-moon forming impact? There are people who actually look at partition coefficients among the Siderfile elements and argue that records, periods of atmosphere or no atmosphere in the early Earth history.
Right? Could you
So people
explicate?
suggest that because of the temperature dependence of partition coefficients between metal and silicate for certain Siderfile elements in particular, that looking at the oldest rocks and their Siderfile element abundances might record some record of a period of atmosphere or less atmosphere in the earlier. And I wondered if you've incorporated anything like that or how that might affect
Well,
your
I
models.
certainly haven't, because I don't even understand the question.
Oh,
So I haven't taken into account. I'm aware that people study siderophile elements in their partitioning between mantle and core, and they tend to like a relatively low temperature
mhm.
for this partitioning to occur.
Low temperature, low
but-
oxygen fugacity.
And what?
Low oxygen fugacity.
Well,
so-
you've got iron around, you're going to have a low oxygen fugacity. I don't think that'll be a tricky thing to get. You got these blobs of iron falling through the mantle, after all, during the times when you're actually doing the partitioning. But I don't know how to put it. I haven't felt that that line of research has converged to an answer yet. I keep seeing people arguing over very basic things.
Okay, thank you. Are there other questions?
You mentioned that angular momentum conservation of energy really constrains your problem. So do you assume that Theia, I guess is the impacting body, was in Earth's neighborhood? Is there not a
I
possibility
don't do the
that it-
collisions. I don't do the collision calculations myself. I merely report. Knupp and Asfog are the people who did them. And there are other issues that are quite germane to what you just brought up. But a relatively low impact velocity does imply a fairly similar orbit to Earth's, yes. There are much more profound problems dealing with the oxygen isotopes, which you may be aware of, that oxygen has 3 isotopes, so you can separate genetic relationships with mass fractionation. So with the 3 isotopes, you can determine whether 2 reservoirs are genetically the same, even though they may have evolved. And the moon and the Earth are identical to measurement accuracy, which is not the case for Mars. It's different. Or the case for Vesta, which is different. Or the case for meteorites, which are different. And the puzzle is, how would it be that 2 planets colliding with each other would then end up with the same oxygen isotopes? Why would the moon be the same as the Earth? That is a profound problem, and it has not been solved.
Okay, thanks.
Okay, I guess I'd like to thank the speaker one more time, and if people have additional questions, please come up and talk with them afterwards. Thank you, Kevin.